Electric flux is independent of size and shape of the Gaussian. In this lecture, I will not cover this, the shape independence. So I'm only going to discuss the size dependence. So here we go. Size dependence. According to Gauss's law, if an enclosed charge is fixed, then the flux must also be constant. So writing this down, Gauss's law states that if the enclosed charge is fixed, that means it's constant. Then the flux must also be constant. And there's only two variables. So that means they have to be inversely proportional to each other. So Gauss's law says that if I have Q enclosed and this quantity is a constant, well, we know that this has to be proportional to the electric flux. So that has to be the electric field times A, the area. But as long as I keep that constant, I can manipulate E and A to keep that. So that's what we really want to show. So the way we'll do this here is that suppose we have two different size spherical Gaussians. Where one of the spheres has twice the radius of the other. So in other words, I'm going to choose, let's say, the second radius to be twice the radius of the first one. So why pick 2? Well, it just makes the numbers come out nicely. That's all. So it's not really important about it. I could have picked 3, but the numbers don't come out as nice. That's all. So it's not a big deal. So now let's enclose a positive charge into both Gaussians. So if I picked a small one, we would expect, so that means here that if we have a smaller Gaussian, we would expect a stronger field there, but smaller surface area. On the other hand, if I look at the larger Gaussian, then I'm going to have a weaker field strength, but a larger surface area. So that means this proportionality has to be just right. In other words, if I'm talking about the electric flux and this guy is a constant, are these guys set up just right that I could pick this such that that is the case? That's really what we're trying to answer here. So now let's go to the picture. So picture-wise, I'm going to say that I have a Gaussian. And let's say that this is my Gaussian right here. And again, we have an opaque Gaussian, so we don't know what's going on inside. And so when I'm looking at this, all we know is that inside of here is a charge. Now, if I pick the other surface, and you can see here that clearly this is a larger surface. So when I look at this guy, we already know that, once again, I'm saying that this is an opaque surface because we can't see inside. So if I have a charge inside, then what I'm going to expect is that I'm going to have an E field that has to be larger. So physically, I have to have a large electric field. Because this is farther, got to have a smaller field at the surface. However, we can clearly see that if I choose this to be my radius, and I choose this guy right here to also be my radius, you can clearly see that the radii different. As a consequence, we're expecting that this guy's going to have a little area, and this one's going to have a large area. So to make things just a bit nicer here, how about if we call this 1 and we call this 2 in case we have to refer. So in other words, this is the electric field on each of these surfaces. I'm not sure why I wrote an E there. I should have drawn a big A instead. And so in this situation, we're going to call this guy 1, and we're going to call this guy 2. So let's go calculate the flux. So now let's calculate the flux value through both Gaussians. So you could see I have a smaller blue. So I have a smaller blue sphere or blue Gaussian. And then over here, I'm going to have a larger green Gaussian. And we want to calculate these things. So what do I know? I know that the electric field, okay, has to be proportional to 1 over r squared. Do I know whether it's a point charge? Of course I don't. But all fields go off as 1 over r squared, at least in theory. So then I'm going to say that I have E1 for the blue, and this guy's going to be proportional to 1 over r1 squared. So if I have a radius of R1, then this is going to tell me here that I have a radius. For this radius here, I'm going to get something that's proportional to R squared. So if I look at this thing, what I'm really seeing is I'm seeing this. That R is associated with that E. This area is associated to R squared. Now I'm doing the exact same thing here. Now the big difference here is, remember that R2 and R1 are connected as follows here, because we know that that is the case. We cherry pick the value. So if I do the same thing, then I'm going to see here. Now I have my electric field. That electric field is proportional to R2. However, we know that this guy is twice the radius of R1. So if I come in here, I'm really multiplying this by R1, and then I'm going to square this quantity so that in the end, I'm going to get a factor here, which I'm going to write as 1/4 in red just to make it stick out. And then I get R1 all over again. So I'm color coding you because you're seeing that R2 now is 1/4 of the strength of E1. So then this implies here that E2 is then equal to, maybe I shouldn't say equal, is proportional to 1/4 of E1, which is exactly what we expected. We expected a weaker field. We just didn't know by how much. I'm going to do the same thing with the area. So if I look at the area, we could then come in here and write the area, and then of course that depends on the radius squared. But I have to connect it back to R1. So if I do that, I'm going to get 4 pi, and then I'm going to get this special number of 2 times R1 squared. And when I square this out, you can see here that I'm going to get a special number 4 right there because of the radius being squared. And then I get 4 pi, and then I come all the way back to R1 squared. Now I'm going to move this over here because I'm running out of area. So let's move this right here. So this immediately tells me here that this guy, it says here that the area now of RA2, the second surface, this guy is then going to be 4 times the area of 1. Again, that's something that we expected. So right away, just by playing numbers here, we're seeing exactly what we were talking about, but that shouldn't be a surprise because Gauss's law says it's constant. That if the charge is constant, then the flux must be constant and act accordingly. So here we go. Now, okay, so Gauss's law states the following. We clearly see that when I look at the flux of 1, this is going to be proportional to the electric field of 1 times area of 1. And when I do that, we saw that this guy was equal to R1 squared, and then we're going to get, we get the area of 4 pi, and then I get the exact same R1 squared, which in the end gives me a constant of 4 pi. That's a constant value. Now, if I repeat the same process here, If I have the flux of 2, this is telling me that this guy's going to be E2 times that area. Now, if I start playing with this one, now note, I could do this with R2, but that's cheap. So what am I going to do it with? I'm going to do it with the values that we just calculated. So we know that the electric field 2 is a quarter strength, right? It's a quarter strength of the field of R1 or E1. And then I'm going to do the area. If I do the area, I get this exact same pi value, but that's also giving me this guy. As we can see here is that that guy is going to cancel out with that guy, which then leaves me with the exact same constant. So these guys lead to the same final constant. And you could see why I picked the 2, because you see that really, really nice calculation. In other words, for both the given Gaussians, they have the same flux, even though they differ in size. They, no, not they, the flux is independent of size. Of Gaussian. So we can write then that the flux, when it's a constant, can be proportional to a combination of E and A just to keep that constant. So the last thing on Gauss's law here, I want to do a summary of what we've talked about. And it says this. So I see 3 things that we've done. We said the net flux through Gaussian only depends on the enclosed charge. And we saw 2 things here. So the sign of the charge of the charge determines whether it is positive or negative. So if I have Q enclosed, and this is a positive quantity, then that tells me that the flux will also be positive. So this is what we call a positive outward direction. If I have Q enclosed, which is negative, then that tells me that the flux is negative. So I have a negative inward direction. The other thing that we found here is that we talked about the strength of the field. The strength of, maybe I shouldn't say the strength. Well, it's too late. The strength of the electric charge determines how much flux pokes through. In other words, if I have a large Q enclosed, then I'm going to have a large flux. If I have a smaller Q enclosed, then I'm going to have a smaller flux. 2 more points here. 2. Charges outside the Gaussian do not contribute to the net flux through the Gaussian. And then finally, but not least, the net electric flux is independent of size and shape of the Gaussian.